Every challenge question, part 8. This is the algebraic methods chapter, chapter 7. Let's do it. So show f of 1 equals 0. We'll just put in 1 and do some maths. It's 0. Put in minus 3. Do some maths. It's 0. This, of course, means that we have factors x minus 1 and x plus 3. Now, I could do some algebraic division here, but I am not going to, because I'm not going to ever, at any point in my life, ever do that. So I'm just going to write the quartic here as a product of x minus 1 times x plus 3 times some quadratic, and I can instantly see that in this quadratic here, a has to be 2, because otherwise how am I getting a 2x to the 4 term, and c has to be minus 18, because this makes it minus 3, and then times minus 18 will give me plus 54. So that's good, and there are loads of ways you could work out b from here, but I just decided to substitute an x equals minus 1, and just if you put that in, you can of course solve the resulting equation for b. After you do a bunch of work, you get b is minus 9, so you get this, and then this quadratic here can factorize to make this. So we have solutions 1 minus 3, as we already saw, minus 3 over 2, and plus 6. And that will be our answer to f of x equals 0. Good. Question number 2 then for the challenge. You've got these 4 coordinates here. We have to assume they're on the same circle. I'm going to assume that they are, and then just show that it works out. The interesting 2 points I can start with is this one and this one. This one represents A, and this one represents B. They're interesting because they have the same height, which means they're just completely horizontal away from each other. And the midpoint, of course, of the two of them is going to be 3, 8, just the midpoint of these two. But that means the center, which needs to make a right angle with this chord here, is going to also lie on the x-coordinate of 3. The center's going to be down here at 3 something. So that's cool. So I can write down my equation of the circle like this. And now what I'm going to do is I'm just going to put 2 of the points in here to solve for b and r. So I'll just put in a here, and I'll also put in, which was the other one that I decided to put in, I decided to put in c here. And you get b and r because you could, or after you do a bit of expansion and stuff, you could do this one, take away this one to get this. And then, of course, you can get b as 5. And then you can substitute b as 5 into here to find r squared really is 25. And now I can say, well, my hypothesis, if all 4 of these points were on the circle would have to be x minus 3 squared plus y minus 5 squared equals 25 squared, or 25, sorry. And now all I have to show is that all 4 of them are indeed on this circle. So I'm just going to put them in one by one, and everything works out, which is great. I mean, it's all just some various plus minus 3 squared plus minus 4 squared. Like, it's just all various arrangements of that. And so they all lie on that circle, so that circle is good. Excellent. Prove that any odd number can be written as difference of squares. Take one square and another square that's immediately above it, and if you take them away, look what happens. It's great. You get this, which is an odd number. So you just choose k to be any integer you want, and this number squared minus this number squared will just give you, you can just generate any odd number that you want at all, which is cool. Good. Next one is a proof of the, it's a really interesting, you can read on Wikipedia just more about it. It's the way that we can bound pi closer and closer. So if you put pi, a circle between 2 squares like this, now pi is defined as the circumference of the circle diameter 1. Just to save me doing any maths, I made the diameter of the circle √2, which makes this side 1 and this side 1 as well, because of the 1, 1 right-angled triangle, √2 right-angled triangle, which means the perimeter of the smaller circle is 4, smaller square is 4, and the perimeter of the larger square obviously is √2 plus √2 plus √2 plus √2, which is 4√2. Now the circumference of the circle is just √2 pi, because of course it's got to be proportional. We're just talking about lengths here. So if you go from 1 to √2 as your diameter, you just go from 1 pi to √2 pi. And then, of course, we can trap, because this circle has clearly got a bigger diameter or bigger circumference or perimeter than the smaller square, but less than the bigger square. You can just trap this between that and that. And then if you divide by √2, you get what they wanted you to get. And now by considering hexagons instead, you can get a more accurate boundary. So here is a smaller hexagon inside the circle and a bigger one. I'll actually make the diameter of the circle 1 this time. Of course, a hexagon is great because it's just 6 equilateral triangles. The circumference, by the way, is pi, of course, which I'm going to trap between the smallest hexagon and the bigger one. This is clearly a half because it's the radius of a circle, diameter 1. Like I said, all of these are equilateral triangles because the interior angle of a regular hexagon is 120, so these are 60. But if that's a half and this is 60 and this is 60 as well, that means this is a half. And so the perimeter of the hexagon is just 6 times a half, which is 3. So that's good. That would be my lower bound. And then the upper bound, you can say, well, this distance down to the bottom here is a half. If you draw another arrow this way, like I said, interior angle of regular hexagon is 120. So this angle is 60. So therefore, tan 60 is a half over this length here, which I'll just call L. Now, I don't actually want L. I want 2L, right? The length of one of these sides. So that's cool because the 2 can jump down here and I'll immediately find 2L is 1 over root 3. And so the perimeter of this hexagon is 6 times 1 over root 3, which is 6 over root 3. So pi is trapped between these two values. If you rationalize this, you get that, which will give us our boundary that they wanted us to get. Good. And of course, if you do that with ever increasingly large numbered regular hexagons with an increasingly large number of sides, you can bound pi more and more accurately between two things, which can, allow you to find pi to more decimal places, I guess. Cool. Prove factor theorem this way around, I guess. It only wants me to do it one way. I don't care about any of this here. I'm just going to say f of x equals this times some other polynomial plus some remainder, because of course this is how division works, right? Like if you're doing 80 divided by 6, what you're actually doing is saying 80 equals 6 times something plus some remainder. So this is just how division works, I guess, in this way. But it's told me that f of p is 0. So, okay, so 0 equals f of p, which equals p minus p times g of p, that should be a p, sorry, plus r. But of course, 0 equals, well, p minus p is 0, so all this goes away. So you just get 0 equals 0 plus r, which means r is 0. And so therefore, if the remainder is 0, that means that x minus p was a factor of this, because it's literally this times this makes this. So x minus p is a factor. Because it divides with remainder 0 is the way that you can finish that off. I think that will do, and I think that's every question in the chapter.